Hi everyone, I'm Xiaoyu. Today I'm going to introduce our paper for open vocabulary 3D segmentation. In this work, we leverage a text-to-image diffusion model as a feature encoder and fine-tune it for different open vocabulary perception tasks. For the problem definition, we fine-tune a 2D diffusion model for open vocabulary 3D semantic understanding. This work addresses several downstream tasks, including long-tailed semantic segmentation and visual grounding. Given a text prompt describing an object's category, attributes, or spatial relations, our goal is to localize the object within the 3D scene. Existing open vocabulary 3D perception models can be mainly divided into two branches. The first branch directly minimizes the per-point feature distance between the cliff-based model and the twinned 3D model, as shown in Figure A here. The second branch uses a 3D mask proposal network, which needs to be trained on labeled 3D data to produce class-agnostic masks. And then the model pulls corresponding representations from the clip feature map. Different from previous methods, we propose a mask distillation method, which is called diffusion to scene. We use stable diffusion as a feature encoder, and we perform mask-based distillation. Our motivation for using stable diffusion is that clip model is optimized for global representation, while diffusion models have shown to be good at local representations. Fine-grained local representation is the key for dense prediction tasks, such as semantic segmentation. Our model leverages the semantically rich embeddings from the 2D foundation models and the accurate masks from the 3D models, and thus our model can achieve better performance compared to previous methods. Our model contains two branches. The 2D branch takes multi-view RGB images as inputs, and uses a pre-trained text-to-image diffusion model as a feature encoder. Then we add a mask generator head, which takes the upsampling layers from the diffusion unit, and then predict a set of 2D masks and mask embeddings. The 3D branch takes the 3D point clouds as inputs and produces high-resolution 3D feature maps. The 2D mask embeddings are used as semantic queries. Specifically, we compute the cosine similarity between each of the 2D mask embeddings and the 3D feature to generate a heat map for 3D masks. Finally, we use a mask distillation loss to force the 2D and 3D branch to make consistent predictions. For the experimental results, we evaluate our model on common 3D semantic segmentation benchmarks, including ScanNet, Maple3D, ScanNet 200, and Replica. We observe that our model outperforms previous methods, which use clip model as a feature backbone. Besides, while there are still a large domain gap between the fully supervised and open vocabulary models, we observe that the performance for tail categories have been largely reduced. Next, we present visualizations of our visual grounding results. Our model can localize objects given arbitrary text prompts. These prompts may describe the object's appearance, like a red short box, spatial location, such as a trash can next to the desk, or usage, like a blue waste basket potentially for recycling. That's all about my presentation. Thank you for your attention.